In the beginning of chapter 5, let's review what is a beam and how to determine the V and M diagrams. Okay, so we study beams in this chapter, and we will determine the bending stress in beams. Okay, in chapter 5. Okay, beams are just members that are slender and support loadings that are applied perpendicular to their longitudinal axis, and these elements are called beams. Okay, this is different from the elements we talked about previously, since we have talked about torsional elements and axially loaded elements. Right? So axially loaded elements, this is the external force added along the longitudinal axis. Right? The torsional elements, we add the load, which is we bend, we twist the shafts, right, about their longitudinal axis. But for beams, we add load perpendicular to their longitudinal axis. Okay, these are totally different. So in general, beams are long and straight and have constant cross-sectional areas. Often they're classified as to how they are supported. Okay, here I showed three different types of beams. The first one is called a simply supported beam. Okay, this one is pinned at one end and roller supported at the other end. What do these support types mean? Pin support, as shown here. Okay, this is the pin support. This means is reaction forces will include a Fy y direction and Fx in x direction. Right? Is there any rotation, any bending moment at this point? No. Okay, a pin support is free to rotation. How about a roller support? A roller support only carries, only has the reaction forces in one direction, that is in the y direction. Right. So the second type is called cantilever beam. The cantilever beam is fixed at one end and free at the other end. Okay, the fixed end condition means that you have a y direction and a x and a bending moment. Right. So you have three reaction forces. And we also have overhanging beam. Overhanging beam has one or both of its ends freely extended over the supported beam, over the supports. Okay, so in this example given here, the overhanging beam, we have only one end extended. Okay, so in this case, you just still have one end pinned. So you have two reaction forces and a roller support, one reaction force, and the left end is freely extended. Okay, in most of the cases, this kind of overhanging beams can be split into two parts and can be considered as combination of a cantilever beam and a simply supported beam under some additional rules, some additional principles that we will talk about in later sections. Okay. So, how to draw the V and M diagrams? As we have emphasized, this V and M diagrams will be very important for these three chapters, because you will at least need to determine where you have the largest values of shear and moment. Okay, so in a loaded beam, in a complicatedly loaded beam, so your V and M in a beam may not be constant or distributed continuously because of multiple loadings that are applied on this beam. So we need to draw this V and M diagrams to do a better analysis. Okay, before everything, let's look at the sign conventions. The sign conventions are shown here. A positive internal shear force, V, acts downwards on the right-hand face of a beam and acts upwards on the left-hand face of a beam. Okay, as shown here. Okay, this means if you have a a beam like this, and you just load it in any way. Then you cut it from here, and you get a right hand face and a left hand face, right? So on this right hand face, if you have a downward V, so that will be positive, right? On the left hand face, you have your upward V, that will be positive. Okay. Of course, on the right hand face, if your V is upward, it will be negative, right? So downward on the left hand face will be negative. Okay, meaning that if we have a V in this direction, that will be negative. And on the left hand face, if you have a V in this direction, that will be negative. Okay, then a positive internal bending moment M acts counterclockwise on the right hand face in a beam. That's shown here. Right, this is a positive M, and acts clockwise on its left hand face of a beam. This is also a positive moment. And if on the right hand face, your bending moment is in this direction, that will be negative. On the left hand face, if your bending moment is in counterclockwise direction, that will be negative. In another sense, if we're observing a beam element, a small segment, okay, a positive internal shear force V causes a beam element to rotate clockwise. Okay, since we mentioned that a positive V acting on the left hand face will be pointing upward, and on the right hand face will be pointing downward. So under the action of this couple of shear force, these elements will be rotating clockwise, right? So this is a positive couple of shear force. Then in the opposite direction, a couple of negative V will be rotating this element counterclockwise. Right. So bending moments acting on a beam element, a positive bending moment, internal bending moment acting on a beam element, will bend this beam element concave upward. Concave upward, that's shown here. Of course, a negative internal bending moment M will bend this beam in the opposite direction, convex upwards or concave downwards, right, as shown here. Okay, actually, I have a better method to remember this sign convention of the positive bending moment. Okay, look at the shape. This positive internal bending moment M will bend this beam element and make it smile, right? And this negative bending moment will make this element cry. Okay, so this is easier to remember this, right? It's, because positive always means something making you happy, so you will smile, right? So positive bending moment will make your beam element smile, and negative bending moment will make it cry. Okay, this is much easier to be remembered, I believe. Okay, then how to draw the V and M diagrams? Okay, these are the steps, general steps I copied from the textbook of statics. Okay, you can review these steps by yourself. I will just briefly go through these steps. Okay, determine how to draw this V and M diagrams. First of all, we need to determine the reaction forces, right? All the reaction forces based on the external loadings. Okay, so step one, we release all the restraints and put reaction forces, Right, then we use equilibrium equations to determine reaction forces. And during this process, as I have introduced, have emphasized, reviewed, if you have a pin support, then you will have AX, AY. When you have a roller support, only AY. And when you have a fixed end, you have three reaction forces, AX, AY, and a bending moment M. Right? So it's, be familiar with these principles. Then we will start from the left side of the structure and build up the shear diagram, then moment diagram, step by step, following some general rules. Okay, these are important. We normally start from left, right? Start from left hand side and moving step by step to the right hand side, and we will build up the shear diagram first, then moment diagram. Okay, since we will need this shear diagram to calculate areas, then to determine the moment diagrams. Okay, so this first rule, start from left. Second rule is a shear diagram first, then moment diagram. Okay, then let's see how to draw the shear diagram. Okay, the rule number one is that at the very beginning of the beam, normally the left beginning, right, this is from the left hand side, the left end. So we start from the left end. The initial shear value is 0 if the structure is not restrained and there is no external forces at this point. Okay, and the shear is equal to the external force or reaction force otherwise. Okay, just after the analysis, you will definitely know what is happening at the left end. Is there any internal force, reaction force, or external force? You will definitely know that. Okay, if nothing, then it's 0. If there is something, just equal that value. Okay, then we will start from the left end, and you determine the initial value. Then we will change this value of shear force from this point to the next point, and this change is equal to the area of the continuous loading between these 2 points. Okay, if between these 2 points you have some kind of distributed load, continuously distributed load, right? So you will be able to calculate its area. The area just means the area below this distribution. In the case of a constant distributed load, as shown here, right? So this area is just equals W times L. Okay, this is the area. Then the rule number 3 will be an external concentrated force cause a jump in shear diagram. The upward force make an upward jump in the shear diagram, and downward force cause a downward jump in the shear diagram. Okay, so we will practice all of these rules later in the example. Okay, then you will draw this moment diagram based on the shear diagram. Okay, the rule number 1 at the very beginning, normally just the left end again. This is from the left end. Initial moment value is 0 if the structure is not restrained by a fixed support, and there is no fixed support, and there is no external moment at this point. The initial shear is equal to the external moment or reaction moment otherwise. Then the rule number 2, change in bending moment from point A to B. Of course, we normally start from the left end, but from any random moment A to the next to the next point B, this change is equal to the area under the shear diagram. Okay, let's see here. So if we have point A here, point B here, the change in bending moment between these 2 points will be equal to the area A1 in the shear diagram. Then rule number 3, an external concentrated moment causes a jump in a bending in the moment diagram. A clockwise moment causes upward jump, and a counterclockwise moment causes downward jump. How to understand this? Okay, after point B, right? This is point B here. So after point B, so if at point B we have a counterclockwise moment, then after point B, look at this beam section. After point B, will it be smiling or crying? So this will be crying, right? After point B, this MB will make this section crying. So this will be a negative thing, so downward jump. Okay, this will be a downward jump. If it's a clockwise moment, it will make the section after point B smiling, right? So that means after point B, we will have a upward jump, positive upward jump by MB. Okay, then let's look at an example. Okay, in this example, we will practice all of these rules, these principles to draw V and M diagrams.